Today we are going to discuss Ampere's circuital theorem or Ampere's circuital law and some of its application. Now, what is Ampere's circuital law? Using this law, we can find out magnetic field due to current carrying conductor. Previously, we have calculated magnetic field due to current carrying conductor using Biresh law. Similarly, there is another law which is called Ampere's circuital law. Using this law also, we can calculate the magnetic field due to a current carrying conductor. Now, this Ampere's law or Ampere's circuital theorem states that the line integral of the magnetic field around any closed path in free space is equal to permeability of free space times the net current passing through any surface enclosed by the closed path. I am repeating. Ampere's circuital theorem states that the time integral of magnetic field around any closed path in free space is equal to the permeability of free space times the net current passing through any surface enclosed by the closed path. Let us say this is a current carrying conductor and we take a closed path this. This is a closed path C. Let us say I current is flowing through this conductor and we take a closed path C. Now, due to this current, there is a magnetic field. Now, if we calculate the line integral of the magnetic field around this closed path, then that will be the permeability times the current enclosed by this path. Right? If B is the magnetic field and dl is an elementary path, then closed integral B dot dl is the line integral of the magnetic field around the closed path C, and which is equals to mu naught I. I is the total current or net current enclosed by this closed path, or you can say I is the net current flowing through any surface enclosed by this closed path. Mu naught is the permeability of free space and I is the, rather I can be written as I enclose, ENC. That means I is the current enclosed by the closed path C. This is the Ampere's circuital theorem, and this expression is called the integral form of Ampere's circuital theorem or Ampere's circuital law. Now, we are going to prove, or we are going to prove this law using an infinite straight current. Let us consider an infinitely long straight current carrying conductor carrying current I. This is that, right? Now, we already know from Biresh law that the magnetic field lines or Biresh law or any other, let us say using the thumb rule or using the Ampere swimming rule, we can say that field lines due to this current carrying conductor will be concentric circles, right? Whose center will be on the conducting wire. The magnetic field due to this current carrying conductor at a distance A is given by, we have already calculated that. If we take a circular path, let us say we take a circular path of radius A, and at this point, what will be the magnetic field? Do you know? Have we calculated that? Magnetic field due to an infinitely long current carrying conductor at a distance A from the conductor, the magnetic field will be?
Mu naught I by 2 pi A.
Good. That means B, here B is mu naught by 4 pi into 2I by A. You have rightly said mu naught I divided by 2 pi A. That is equal to mu naught by 4 pi 2I by A. And this B is always tangential to this closed line. Right? Therefore, we can say B dot dl is equal to B dl cos of 0. That means B dl. Since in every dl element, B and dl are parallel. B is the magnetic field. Magnetic field is always parallel to the line element, right? Line element, that is dl. That's why we have written B dl into cos 0, that is B dl. Therefore, if we calculate closed integration B dl, then it will be closed integration over C B dl, and that is equals to closed integration B is mu naught by 4 pi 2I by A into dl. Now see here, A is the radius of the circular path, constant, I is the current, constant, mu naught is constant, 4 pi is constant. All can be taken outside the integration. BIA closed integration dl, and closed integration dl is the circumference of this circle, that is total length of the path. Total length of the path is equal to circumference of the circular path, that is 2 pi a. Now here see here, a cancels out, pi cancels out, 2 4 and 4 cancels out. That's why we get mu naught into I. Now closed integration B dot dl over the path C is equal to mu naught I. I is the total current enclosed by the path C, which is the Ampere's circuital law. Now this Ampere's circuital theorem holds good for a closed path of any size and shape. You can take this path any shape and size. For all type of path, this theorem is valid, right? This theorem is valid because the relation, which is the relation, this is the relation, right? Because the relation is independent of the distance, independent of the distance A. But this law is not independent of Biresh law. It is interrelated. Rather, you can say Ampere's circuital theorem is another form of Biresh law. You can say both laws connect the magnetic field and what? Current. Biresh law also deals with the magnetic field and the current, and this Ampere's circuital theorem is also deals with the magnetic field and the current. In fact, both the laws gives same physical result of electric current, but in two different ways. There is some limitations of this Ampere's law. This Ampere's law is not a universal law. You cannot apply anywhere. You cannot apply in any cases or in all cases. Like I give you one example. We have calculated magnetic field at the center of a circular coil using the Biresh law. That was what? Mu naught I by 2r, right?
Yes.
At the center, right? But applying Ampere's law, you cannot find the magnetic field at the center of a circular coil. Do you find? No, you cannot assume the Amperean loop. This is called the Amperean loop. That is the closed path, because center is a point. And second thing is that this is one limitation, right? This law cannot be used in every cases or in every way. And second thing is very important, that is this Ampere's law deals with only the steady currents. If the current is time varying, time dependent, then this Ampere's law is not valid. We will in later time or later classes we will discuss. You have to do a correction. You have to add another term which is called the displacement current to the Ampere's law, and that is called the Ampere-Maxwell law. We will discuss in later classes. Right. Now these are the statement and proof and the limitation of the Ampere circuital theory.